So on Saturday, there's no bell, right?
Oh, good.
Okay. Good morning, everyone. So we are happy that it's a very new experience for me because it is the first time I host a lecture on Saturday. But I'm very happy to see all of you here. That's because you all love physics, okay? And that's very good. Today is we have 2 more lectures on thermal symmetry. So we know the small world we don't have. Maybe we have nearly perfect thermal symmetry, but in big worlds we don't have. So which means you should cherish and enjoy the last 2 lectures. Okay. So let's welcome Frank Wilczek.
Thank you. Thank you, Xingdong. Thank you. Thanks for coming out on this beautiful Saturday morning. I'm going to pick up pretty much where we left off. We had motivated the existence of a new particle, a qualitatively new kind of particle, which we call axion. Let me give this lecture will be primarily about the state of experimental searching for axion, which is now at a very, very interesting stage. To set the context, let me remind you that axions are very light but very weakly coupled particles, and because of that, they do unusual things, and a variety of different kinds of experiments have been, and astronomical observations have been considered in order to shed light on the possible existence of axions. And this is an incomplete list. And this is a slightly out-of-date summary of the state of things. This doesn't work.
The light?
The light doesn't work. Yeah.
Maybe use a classical pointer.
Yes. Oh, yes. I like this anyway. All right. So I showed this briefly before. Let me just point out a couple of things that I would like to add. One is on the right hand, on the lower axis, you have the mass of the axion. And remember, the mass of the axion was given by the QCD scale divided by that parameter f, the scale at which you have the breaking of Peccei-Quinn symmetry. And the QCD scale is something like 100 MeV, so 10 to the 8th electron volts. If we consider symmetry breaking at the weak scale, so we have Higgs particles breaking the Peccei-Quinn symmetry, as in the original model that I showed you yesterday, then those vacuum expectation values would be perhaps 10 to the 3 GeV, roughly. So we have 10 to the minus 2 GeV divided by 10 to the 3 GeV. That's 10 to the minus 5 GeV, or 10 to the 4th electron volts. So weak scale axions would be over here or so on this line, or maybe over here if we are generous about what we modeling with the Higgs field. And you see that they are very ruled out by a variety of astronomical observations. They could cause, their decays cause X-rays and an extragalactic background of light. They affect Big Bang nucleosynthesis because they're relatively weak, strongly interacting. Remember, the interactions go like 1 over f. So not strongly interacting in the sense of strong interactions, but much more strongly interacting than axions would be if their masses are over here. They would be emitted from the supernova. They would cause ionization, and they would affect stellar evolution. There are also some, if we go away from the weak scale, we raise the scale of Paget-Quinn symmetry breaking, then we move here, and you see there's much less in the way of constraints, because although the particles are light, they interact very, very weakly with matter, and so all these astronomical effects are much less, and are consistent. The existence of these particles is consistent with observations. This one, CAST, is an experimental effort to look for axions coming from the sun. It's basically this, which we mentioned. Oops. These are a bunch of other kinds of astronomical observations. Cooling of neutron stars is something that axions could do, but again, not if they are the axions predicted by QCD, which have the parameters along this line. And some of these are experimental efforts. The CAST experiment I showed you a picture of, or actually the second generation CAST experiment is what you saw in that big picture. And then there are a variety of experiments of the general type that I'll be describing in these lectures, which are special antennas designed to pick up the signal of a cosmic axion background. And then there are other exotic effects on black hole physics that constrain the properties of axions. But there's a big, big, fat region that's possible space of parameters where the axion could have eluded observation so far. And you see people are working to get into that region, and we'll see that there's a particularly favored region where the axions will be predicted to form the dark matter of the universe. So let's get on to the well, I shouldn't say necessarily the most promising, but I think it is the most promising way to look for axions, which is to look at the cosmic relic radiation, the kind of fluid of axions that pervades the universe when you work out how they get produced and processed through the Big Bang and the evolution of the universe. This was the basic picture. This is a particular point in space, and as a function of time, the value of the axion field, which is associated with a complex scalar field that has a magnitude and a phase. The axion proper is the phase field, but it comes together with a magnitude. And as the universe evolves, it starts out at a high value. There's a lot of thermal radiation around, and well, you'll see how it will spell out how it evolves in equations momentarily, but it gradually wants to settle down to the energy minimum, where we saw the theta parameter comes to be very, very small, which is the whole point of the axion, is to explain that fact, which is otherwise mysterious. So let's work out that cosmology. It's very instructive, and it's a very pretty exercise in basic Big Bang cosmology. So at some very high temperature of order F, which is the characteristic scale of the symmetry breaking, so energies of order F are involved. F is a mass scale. Everything is a mass, and these units where h bar equals c equals 1. So the temperature is also a mass. We could expect the phase transition to occur at that kind of temperature. And then once the symmetry is broken, our complex scalar field, which has the axion as a phase, remember this is theta is actually the axion field properly normalized divided by F. At that Peccei-Quinn phase transition, we have energy stored in the value of theta if it's not at the effective minimum of the potential, which we saw is roughly proportional to F sine squared theta. There's the minimum of the potential, and then you oscillate around it. So this is a representation of the fact that you're away from the minimum. Okay. I think we wrote it as 1 minus cosine theta, but if you use trigonometric identities, it's essentially like this. There's a sine squared theta over 2 or something. We're not going to worry about that. Okay, so the order parameter field will settle, we'll see, close to the bottom of the well. Hit it better if the axion is going to do its job. But there are residual oscillations in its phase. And because the field is so stiff, because there's this big parameter that appears multiplying the energy density, F, even small angles can correspond to a lot of energy density as far as cosmology is concerned. And that's what the axion background is. Okay. Now, we will show that the residual mass density is proportional to the original mass density. It goes like F sine squared theta. Let's work out the cosmology in equations. Okay, so what we're doing is considering the expansion of the universe and the evolution of a scalar field. And I've changed, this is just a generic scalar field. This is a real field, so this would be the axion itself, not the complex field from which it derives. Okay, and then the prescription for including gravity, how the scalar field couples to gravity, is you put in the measure square root of g, and then you use the metric tensor to contract the space and time derivatives that occur in its kinetic term. That's it. Okay. So from that, everything flows because we can set up the equations. In an expanding universe, we have this metric. Okay, so the time derivative is normal, but we have it expanding spatial scale. Okay, so then the square root of g is the square root of the product of all these things, and that's a cubed. We put that, and then the equations of motion tell us that we take the second time derivative, that's equal to the derivative with respect to the scalar field itself. So this was dl by d phi dot, and this is dl by d phi. So this is basically F equals ma. Okay. And now if we put the form of square root of g and g0 that we have from the background expanding universe into this equation of motion for the scalar field, we get a very elegant result that it looks like a damped harmonic oscillator. Okay. So there's the oscillations here of magnitude. We're ignoring, I should mention, implicitly ignoring any possible scalar gradients in the scalar field. And the reason for that is that as the universe expands, those will all get stretched out and go to zero. I'm oversimplifying quite a bit, but this is a good starting point for more refined considerations. All right, so we have a damped oscillator whose damping coefficient is changing with time because the universe evolves and the rate of expansion might change with time. And also the effective mass might change because the axion field is interacting with everything around it, and you have lots of hot gluons and things like that, and that affects its mass. So there's a mass that's a function of the surrounding temperature, which is going down as the universe expands. Okay, so now you can calculate the axion mass because we know what the relevant interactions are. If you can calculate in terms of the fundamental degrees of freedom of QCD, the interactions of the gluons with the gluons and with the quarks that motivated the axion theory in the first place are quite precisely prescribed once you know what F is. So then it's a calculation that can be done crudely by hand, but also accurately using supercomputers. Now we know how to do this kind of thing in QCD, and the result is that the mass goes up, the mass of the axion, that is, goes up as the temperature goes down and then plateaus when QCD kind of settles down at 100 MeV. So when the temperature is more than 100 MeV, the gluons and quarks are kind of moving freely. They're not organized into hadrons. And so you have one regime where you can calculate in terms of, roughly speaking, in terms of semi-classical field configurations, so-called hot QCD. But then when you go into this regime, the axion mass of confinement and ordinary sort of laboratory QCD as we observe it, then the axion mass levels out. Okay. Remember, we had a damped harmonic oscillator. When the damping term dominates the potential term that wants to make it move, the field is stuck. We're overdamped. So early in its history, when the universe is expanding rapidly, and remember the axion mass was just ramping up, the field will be stuck. Then we enter a regime where it's not stuck, where both terms become important, okay? Where it's damped, but it's still oscillating, okay? So In that case, we write the field as an amplitude and an oscillating piece. Okay, we're going to have the oscillations now overcoming the damping. Okay, so then if we write this equation in terms of big A and M, we'll have the 0th order term, which is assuming A equals, which assumes A doesn't change. But then we'll have slow changes in the amplitude. So that'll just be the oscillation terms. Then we have out of phase terms, the frictional terms, if you like, which we obtain by looking at the things that are first order in time derivatives. And if you look at this equation, it can be organized to give you a famous result of classical mechanics, the so-called adiabatic invariant, that says that the amplitude of the oscillations, or the action in an oscillation, stays the same. So if you calculate not the energy, but the action, that's an invariant of the adiabatic evolution of this scalar field or harmonic oscillator. Okay, so energy is not conserved because you have a time-dependent mass, but what is conserved is this adiabatic invariant, the amplitude. So the energy would be, the energy density would be a squared m squared, but here you see we have only a squared m appearing. And so as the mass goes up, the energy goes down. Let me go back to the picture here. So we talked about the mass, how it develops. The expansion of the universe means that the A dot over A term is going like this. The rate of expansion of the universe is going down as a function of time. It was expanding faster earlier on. And so you see that these lines, so here we're in the overdamped regime where the A dot over A, that effective viscosity, is dominating the mass, which wants the field to oscillate. But then eventually they cross. Then you have an adiabatic regime until finally the mass levels out. So there are 3 different regimes we have to join in to figure out the evolution of this scalar field and the density associated with it. So we're just solving that equation. Whoops. The amount of energy that's in play in the axion field was the QCD scale to the 4th. We have an effect of adiabatic damping, which, as I mentioned, means the energy density goes down during the adiabatic regime, which starts at when Ma is equal to 8, the Hubble constant, the rate of expansion of the universe, but then sets in when these two are equal, but then the mass goes up and we get this damping factor relative to what we would have for free development of the field. If we had free development of the field, we would just have the density going down like the radius cubed, or 1 over the temperature cubed in the expansion of the universe. And so at that point, once the mass is frozen and once the mass is static and the damping is no longer important, then we have essentially a gas of particles. We just have free motion of this field. It just oscillates at the mass of the particles. So this is a representation of the three important factors. We start off with this kind of energy density, and it's frozen in because the field, then we get the adiabatic damping, and then finally we get the expansion, the dilution of particles just by the expansion of the universe once we have the particle interpretation. Okay. And then putting what this is in terms of what this factor is in terms of fundamental parameters, the expansion, the Hubble parameter, when we have the QCD scale getting equal to the cosmological scale, is lambda squared over m Planck. That's the rate of expansion of the universe when the temperature is of order lambda. At that time, the mass of the axion is lambda squared over f, and so this damping factor analytically is f over the Planck scale. It's the ratio of the coupling of the scale of axion physics is f divided by the scale of gravity, which is the Planck scale. If that goes by a little fast, let me refer again to the picture. You get a surprising result out of this, I should say. You find that the net density is proportional to F, even though the axion mass is inversely proportional to F. Okay, so as F increases, the axion mass goes down, but you produce enough more of axions that the net density goes up. And that was a surprising result when we first derived it, but follows very nicely from this picture. The point is, when you have a larger value of mass, the adiabatic regime, where these lines cross, sets in sooner, and you have more adiabatic damping. Okay. So you can understand the qualitative result very clearly just by looking at this diagram. So this is how the mass goes, this is how the expansion of the universe goes, and this is following the calculation that I just outlined of how the density evolves, how the energy density evolves. Okay, so that's the fundamental result. And I should make one more clarification, which is that that diagram that I got off the internet of the particle, of the value of the field coming down and rolling around many times as it comes to the bottom, is not right. The way it actually evolves is highly overdamped. So it comes down more or less straight and then oscillates around a little bit around the minimum. So it's strongly overdamped in the early universe, and that's important because it remembers the initial value of sine squared theta 0 of the initial displacement. Okay, and that sets the scale for the subsequent value of the axion density. Okay, so the takeaway formula here is you get a calculable coefficient times an axion density, which is roughly F times sine squared theta 0. The initial energy storage gets diluted by the factors we just computed. Okay, so now there are two scenarios for how the early universe might have evolved that are relevant for assessing the present-day axion density. One is conventional cosmology, so we will ignore the possibility of inflation of the universe. We will not allow dark energy, if you like, or a cosmological term to dominate the evolution for any significant period, interrupting the calculation we just showed. So once the phase transition to, once the Peccei-Quinn phase transition has occurred, once we get to the scale F, we don't have inflation after that. Okay, that's the classic axion cosmology. Okay, which means that the evolution of the universe since the Peccei-Quinn phase transition, since axion sort of became a thing, is conventional. And then we have a very interesting phenomenon that's easy to understand intuitively. At present, when we look out at the sky, we can see only a finite region, because the universe has a finite age and light can travel only at the speed of light, or anything else can only travel at the speed of light. And that means, at most, that means that we have a so-called horizon. It means that the part of the universe we can survey depends on time, and as time unfolds, we get to see more and more. But that means there were pieces we couldn't see before, that we can see today that we couldn't have seen yesterday. Extending that back to these very, very early times when the Peccei-Quinn transition occurred, and these displacements, initial displacements of the axion field from its minimum were set. When we look out at the sky, we see many early universes that couldn't talk to each other, that didn't have horizons large enough in order to communicate with each other, to see each other at all. So they're not what's called causally connected. That means if we look out at the present-day sky, we get a sample of different values of the initial offset sine squared theta 0. We get a random sample. And if I remember correctly, if you take if you actually calculate how big the horizon was at these very early times, you find that there are tens of thousands of samples of different universes at that time that we get to see today. Okay. So we get a good sampling of the possible values of sine squared theta 0, how much this field was initially offset from its true minimum. Okay. By the way, you might say, well, why didn't it prefer to go to the true minimum? The point is that the amount of energy that was locked up in this kind of energy field in the axion is much, much less than the ambient thermal energies. And so it kind of is a random variable. Okay. The present day dark matter density, which is that sort of density, is totally negligible compared to the energy densities that obtained in the early universe. Okay, so if we're looking at many, many different samples that are statistically independent because they were causally disconnected, we should just average over this sine squared theta 0. So that means the only remaining uncertainty in calculating the axion density from fundamental principles is gone. We needed to calculate the sine squared theta 0, and we need its average, which is a half. Right? Easy calculation. And so you take the supercomputer calculations from QCD and accurate timelines of the evolution of the universe, calculate it out, And there are significant complications due to the fact that we've suppressed that the axion field can also change in space. So there's been a long story connected with getting that factor under control. But over time, the modeling of cosmology and also the calculations in fundamental QCD to relate the parameters of the fundamental Lagrangian to the parameters of the observed particles have gotten much more sophisticated. And here's a fairly recent representative of the state of the art. Subsequent work has not changed the main conclusion, but made the error estimates more reliable, maybe, and tightened the estimate. So in the context of the classic axion cosmology, that is no inflation, if you have the Peccei-Quinn transition and then normal Big Bang cosmology after that, then you get a precise estimate for what it takes for the axion field to provide the dark matter, and we pin down the remaining parameter, and it's 4 to 180 microelectron volts is the mass. Okay. For experimental purposes, as you'll see, it's useful to translate that into a frequency. You're going to try to convert these axions pretty much at rest in the cosmos into photons. They will be photons in this kind of microwave region. And that's what's shown here in this blue band. So where the blue band crosses the gold band, that's where the axion dark matter is to be found in the classic cosmology. You take all cosmology and axion physics at face value, you have a fairly unique prediction for where you're supposed to look, and nobody's looked there. See, there have been attempts to look at those frequencies, but they haven't been sensitive enough. There have been more sensitive attempts at lower frequencies, but no one's had the resources or the wit to get into the sweet spot. That's going to change, as you'll see. Okay, before discussing the experimental efforts that are, I think, promised to get us there, I'd like to talk about an alternative form of axion cosmology. Nowadays, there are significant, although indirect, pieces of evidence and rather thin compared to most of Big Bang cosmology, but there is significant evidence for a period of inflation in the early universe, a very, very rapid expansion, accelerating expansion for a while. I'm not going to discuss cosmology in great detail here, but inflation, for our purposes, just means that the universe suddenly got very, very big. And in the context of axion physics, what that can mean is you have the Peccei-Quinn phase transition. So theta zero, the displacement is changing in different places of the universe, and then one particular patch expands enormously. Well, everything expands enormously, but one particular patch becomes the patch that we're in, because we derive from a small patch early on, according to the inflationary universe. That means that instead of getting to average over theta zero, there's just one theta zero that we inhabit. So very, very far away, there will be other values of theta zero, but those parts have been taken away from us by inflation. They've been moved so far away that they're beyond our horizon.
Sorry, when you say small, you just mean to what? small.
Well, they get it means we're sort of in the reverse situation to what I described before. Instead of our horizon being much larger than in the early universe, in inflationary models, our present-day horizon is many orders of magnitudes, typically 10 to the 50th orders of magnitude or so smaller than the horizon back, than the region that was inflated to make a coherent universe. So the correlated volume, the patch that got inflated, has just one value of theta 0, and that now envelops the whole present-day universe. So we don't average. We should just take one value of theta 0, which could be different, and would be different if we were sufficiently far away. So that means that, remember, the overall density was going like f times sine squared theta 0. It means that we can now use values that were previous in the other kind of cosmology were forbidden because you got too much dark matter. It's all right to get too little dark matter in axions, but you can't have too much. That's problematic because you're not going to be able to cancel it off with negative mass. And but now we can accommodate the larger values of f if we keep f sine squared theta appropriately small. So we can have larger values of f as long as we have smaller values of the initial displacement. Now, this is a multiverse scenario. Okay? It means in our neighborhood, which came from an inflationary patch that had one value of theta 0, we have a certain amount of dark matter produced in axions. In other regions that also got inflated, but are now beyond our horizon, outside our original patch, you'll have different values of theta 0, and maybe you'll have larger values of theta 0, and such that those regions contain a higher ratio of dark matter and axions to ordinary matter than we have in our universe. But that's okay, because we're not there. As long as we can consistently live in a patch with a given value of theta 0, logically, we don't have to concern ourselves with those things which are predicted by the theory to be beyond our horizon. And successfully, we haven't seen them. Now, that's not a very satisfying kind of argument if it resulted in us having to arbitrarily choose some parameter to be very small. We had to choose sine squared theta to be very, very small. And there are two things to be said about that. First of all, the values don't have to be all that small. If we remember, we're starting from f of 10 to the 12th being the good value. If, say, we wanted to go to the unification scale, we would just have to take sine squared theta of 10 to the minus 4, which is small, but not absurdly small. However, we can do better than that. We can consider what would life be like in those other parts of the multiverse, other parts where the theta 0 was bigger. Now, in many speculations about the multiverse and so-called anthropic reasoning, it's out of control because you don't know what the effects of changing different parameters are. Like, there are lots of speculations about what would be different if, isn't it amazing that the values of the fundamental parameters we see in our world are so conducive to life? But the problem is we don't know, we don't have a model of how you can pose the counterfactual, what could have been different, and in what pattern you could vary things. But in this case, you absolutely do have a completely closed model where you can consider the effects of this particular kind of variation from place to place. It's just changing the value of theta 0, which translates into just having more or less axion dark matter at present compared to a baryonic matter. And yeah, so we don't have to get involved in more elaborate speculations. We have a model that predicts this kind of pattern. And I think it's very sensible to consider selection effects. That is, we shouldn't ask what a typical volume of space sees, because we're not in a typical volume of space. That would be like saying that life typically, that it's very unusual that life, it's incomprehensible that, or very unlikely that life exists on planets, because planets take up only a very small volume in the universe. Volume is not the right measure. So you can ask, instead of seeing what the typical volume sees, what value of theta 0 the typical volume sees, you can ask what the typical baryon sees, for instance, or you can do more refined estimates along that line, trying to make corrections for the fact that what we observe is not necessarily the most typical volume, because the most typical volume is inhospitable to any kind of observation, not just human, but any kind. So, for instance, if you have a much higher ratio of dark matter to baryonic matter than we have in our universe, then it's very, very difficult to form complex structures. The mass density is totally dominated by this very diffuse dark matter, and it's hard for galaxies to form in a reasonable way, for instance. And if you refine those ideas, you can convince yourself that the actual value of the dark matter density is pretty optimal value for the emergence of, for the possibility of observation. So that's a logically possible and not terribly odious use of the anthropic kind of reasoning, but here much more well justified than in general. It's basically just making what are called a correction for selection effects in astronomy, that the fact that where you're looking makes the difference to what you see, and or your means of looking also can bias the observations. And but there is an objective issue with this alternative, which is if you make the mean value of the axion field unnaturally small, and it's the dark matter, then fluctuations in its value translate directly into fluctuations in the density of dark matter. And because the denominator is chosen to be small, it means the numerator, the relative fluctuations are bigger. And this gives a particular pattern of early universe fluctuations, which you then fold into calculations of the formation of galaxies and astronomy and the development of inhomogeneities in the microwave background. And you find that these kind of correlations of the dark correlations or fluctuations in which the dark matter density changes in a way that's uncorrelated with general fluctuations in the overall density, fluctuations in temperature. These are so-called isocurvature fluctuations, are disfavored by cosmological observations. So there's considerable tension in this alternative cosmology. And I won't be saying much more about it. So this is a good time to pause and see where we are before we go into the experimental aspects of axion physics and T violation generally. So our grand conclusion was that we almost understand T violation as a consequence of deeper principles. But that very success, which is tantalizingly close to a beautiful completed story, is still flawed because we have a very definite loophole identified. And if we close that loophole, we're led to the prediction of a new particle with well-defined and remarkable properties that make it a very good candidate to provide the cosmological dark matter. So we have this coincidence. Think not. And we have a suggestion for how to explain it. Okay, so that was the end of the original planned lecture 3. I can take a couple of questions now, but otherwise I want to move right on to experimental aspects of T violation and
any questions so far?
axions. Yeah.
Hi. Could you please comment on the assumption that the axion mass is generated solely by QCD effect?
Well, the axion mass kind of by construction is due only to QCD effects because of the Peccei-Quinn mechanism that relates the Peccei-Quinn symmetry that basically ensures that the rest of the Lagrangian, besides the quantum mechanical QCD non-perturbative effects associated with topologically non-trivial fluctuations that we discussed so painfully, that's the only source of axion mass.
Right, but in general, the axion has a shift symmetry that is expected to be broken, right, by gravity effect and so on. So what is the meaning of explaining a very small number, like trying to find an explanation for theta term, imposing a shift symmetry to a very high precision?
Well, we're imposing a symmetry to a very high precision, right? The gravitational corrections to this symmetry have never been calculated in a convincing way, and nature seems to be telling us that they're very small.
Okay, more question? Okay. So then Frank can continue.
Okay, so now we're going to switch from high theory, switch gears a little bit to discuss experiments, both about T violation in general, but especially about this frontier of axions. Let's start with the kind of measurement that motivated the postulate of axions in the first place. That is the observed smallness of the neutron and some other electric dipole moments, which we can only understand on the basis of very good approximate T symmetry and in particular a very, very small value of the effective theta parameter. Now, you may remember I left you with a puzzle here that we're very perturbed. We try very hard to measure even a tiny electric dipole moment on a neutron, and say if we found that would make it be a great discovery. It would revolutionize our understanding of fundamental physics. And yet, when you turn to a chemistry book, you find tables of plenty of electric dipole moments, and they're computed inside, and many of them are not zero. So what's going on here? This is a problem that bothered me very much, but I think we can get to the bottom of it now. So when does it make sense to interpret measurements of electric dipole moments as evidence about fundamental T violation It's very important to be clear about that. So let's start by considering a system that has spin 0. Okay, so we'll consider it as a black box. It might be a fundamental particle, or it might be a very complex molecule. But if we take it, if it's a molecule or if it's a particle, we just have to make sure that we probe it with energies small enough that we're separated from anything that reveals it has internal structure. Okay, so the spectrum is just an isolated spin 0, no spin. So there's just a non-degenerate state of separated. It can have kinetic energy, of course, but not internal degrees of freedom. In other words, but objectively, the criterion is simply that you have a gap in the energy spectrum and an isolated state of 0 spin. Okay, so now if you apply an electric field, here's our isolated state. There are other states that might be connected with the Hamiltonian of an electric field, but they're separated by an energy gap, delta. And for sufficiently small e, there's no linear correction to the energy. Or in other words, there's no electric dipole moment. Whether there's T violation or not, there's no possibility of an electric dipole moment in the sense of a response that's linear in the electric field for small e. Okay, I did this using the standard chemistry electric dipole approximation. Really, you should use the standard model in all its glory to calculate, if you really want to calculate accurately, but it doesn't change the conclusion. Okay, now let's consider a more interesting case when the ground state is spin 1/2, still separated by a gap from everything else. So we have spin plus or minus 1/2 states that are degenerate by angular momentum conservation. And now, when we apply an electric field, that's a spin 1 operator, it can connect those two states like that. And now we can have an electric dipole moment. There's nothing about fundamental quantum mechanics or symmetry of rotation symmetry that forbids this. Okay, so there is the possibility of a linear response in energy to an electric field, or in other words, an electric dipole moment. But we showed under very general circumstances that if T symmetry is valid, we have Cramer's theorem that tells us the states always come in degenerate pairs related by time reversal transformations. So if that happens, then there is a principle that tells us that there's no linear response in the energy. There's no such splitting. The splitting vanishes. Not just linear terms, but all terms, as long as you can neglect the higher states. So thus we arrive at a clean and powerful way of testing fundamental T symmetry. We use it. The real test is whether Cramer's theorem is obeyed. And that can be applied to neutrons, electrons, protons, even molecules. And people do try to do fundamental T violation experiments on molecules. They dare to do that because Cramer's theorem, you're really looking for violations of Cramer's theorem. Okay. Another perspective on this is that if the only degree of freedom in play is a spin 1/2 that can interact with the electric field, the only candidate Hamiltonian that's linear in the electric field is sigma dot E, and that violates time reversal. So its coefficient should be 0. But we don't have to appeal to effective Hamiltonians or any kind of approximation. It's Cramer's theorem is the basis, really. And we observe in nature, people have worked very, very hard over decades to try to observe fundamental electric dipole moments. These are, I think, close to, but probably not exactly the best current limits. I haven't updated this slide in a while. So for the neutron, it's a fraction of 10 to the minus 6th e centimeters. And for the electron, it's a few parts in 10 to the minus 31 e centimeters. This is to be compared with a sort of natural scale for internal structure of these particles. That is, you take the Compton wavelength, the dimensionless length you can form from its mass, h bar and c, and in the case of a neutron, it's 10 to the minus 18 centimeters. In the case of the electron, it's 10 to the minus 4 centimeters. And the limit of 10 to the minus 10 on theta is basically comparing this to this. All right, with this. There's an extra 8 orders of magnitude floating around somewhere, 2 orders of magnitude floating around somewhere, but that's where the limit we've been quoting comes from. And a more vivid way of saying this is, okay, if you think of spin as rotation of something, okay, it says that if you, and there are charges inside neutrons. I mean, for sure, neutrons have complex structure with positive and negative quarks and antiquarks coming in. Electrons might or might not have internal structure. That's useful to think about. But in any case, what would be what an electric dipole moment would mean is if you have an electric field and your spinning object, the positive charges want to migrate to one of the poles in preference to the other. Okay, so that may not sound like an intuitively appealing effect, but that's and the reason it's not is that it doesn't appear in nature. We don't see this thing in textbooks because it's just not observed. So rotation does not lead to charge separation. This is a nice intuitive way of putting these constraints, and it really, really, really doesn't. Not even a little bit. Okay, so these limits are basically based on either looking for precession effects induced by electric fields sort of making the spin precess like magnetic fields do, or looking for spectral splittings that would violate Cramer's theorem. So either one of these things, when you analyze it a little deeper, involves violations of Cramer's theorem. Okay, so what are the chemists doing? What the heck are they talking about with these electric dipole moments? Are they those unenlightened souls? Well, when our system has many low energy states, so it's a molecule that could have different shapes, for instance, and we're not looking at the fine structure of the spectrum, so we're looking at possible energy exchanges that take you into many states, then it is not necessarily appropriate to focus only on the lowest lying state as we did, and say there's a gap, so you ignore everything else. On the contrary, the separation of energies can be much smaller than the interaction energies connected with the electric field. So instead of ignoring the effect of the electric field, it can be more appropriate, if you have a lot of close by states, to ignore the splittings between those states. And that's typically what is done implicitly in the chemistry books. So instead of treating the interaction introduced by the electric field as a perturbation, you treat it as the dominant piece of the Hamiltonian. You ignore the splittings between some manifold of low energy states. Or if you want to put it in a more highfalutin language, the interaction energy, which is manifestly proportional to the energy, organizes a responsive state. You diagonalize what used to be a perturbation is now the main Hamiltonian. You diagonalize that, and the spectrum is manifestly proportional to the electric field because that's what you've diagonalized. So going back to the two-state system here, if we take the off-diagonal terms much larger in magnitude than the diagonal terms, then it becomes essentially a linear splitting. Oops. Where am I? What happened? Oh, okay. Yeah, okay. So this is implicit. Can you get back to the main format? Yeah, okay. So a version of this idea is implicit in the treatment of electric dipole moments that you'll find in basic chemistry texts. What they do is fix the position of nuclei and calculate charge distributions. But in reality, nuclei can move, they can rotate. There are lots of low energy states associated with nuclear motion, but they are very low energy states, so there's small splittings associated with them. Applying an electric field gives you interaction energies that dominate. I mean, the electric fields of interest dominate those splittings. So what you should do instead is diagonalize the electric field interaction. And that's particularly useful because in a complicated environment, as is the case in practical chemistry, the dominant interaction, the dominant way the particle interacts with other forms of matter is through electric fields. So having these states, that effective states that diagonalize the electric field interactions, those are the ones that are appropriate when you consider reactions or how things are behaving inside the materials. Okay. Similar remarks apply to magnetic moments, with the important difference that natural environments will still be picking out diagonal states of the electric interaction, and the magnetic interaction is usually subdominant. So you shouldn't be considering the low energy states in vacuum, but the low energy states in the presence of an electric field, and then treat the magnetic field as some kind of perturbation one way. The bottom line is you have to be careful about what you're doing and think about the actual situation that you're trying to analyze. So in general, electric and magnetic moments should be discussed within a context, within a specific framework of what they're being used to do, to discuss the low energy excitations of some kind of states. And in general, there's more to life than ground states characterized by just angular momentum. Okay, so even that's where we do clean tests of time reversal violation based on electric dipole moments, but the chemists can do their thing too, and we can peacefully coexist. And in fact, it's quite interesting. Especially if you go into biology, there are molecules with rings that have low energy excitations that can have dynamical distributions of charge and spin, including currents of both, and those will be chosen by the ambient interactions. And when we want to think about violation of time reversal symmetry in biology, we should be thinking about those situations. So both electric and magnetic moments are fair game. They're not constrained by vacuum symmetries. Okay, so that's what I wanted to say about electric dipole moments. How are we is this an appropriate time to pause now?
Well, what depends yourself. Or maybe you can briefly mention.
Okay, I'll do this one, but then we will break, because after this one comes the big discussion of experiments to look for axions.
Okay, that will be the
an exciting frontier. Okay, so let's consider another way of looking for T violation that's very fundamental. That's to look for new kinds of forces, sometimes called fifth forces, but in any case, forces that come from the exchange of new particles like axions. Okay? But they might be other things too that are mediating new kinds of forces. We have our framework of quantum field theory that makes it possible to consider what are the kind of possible interactions that we've been missing, and how do we look for them. So very light, very feebly interacting particles are an intriguing frontier for fundamental physics. Axions are an outstanding example, but they're not the only one. So if you have a very light particle, its exchange has a range, which is the force associated with its exchange has a range which is controlled by its Compton wavelength. And if the mass is sufficiently small, that the wavelength can be large and affect macroscopic physics. So it's very interesting and instructive to calculate this sort of thing. One nice feature of interactions that violate time reversal symmetry is that the backgrounds are very limited. So if you find a non-zero result, you can start booking your trip to Stockholm. Okay, so a convenient way of going from fundamental quantum field theory formulations to forces is to calculate scattering at very, very low momentum transfer and interpret that, which you can do with Feynman graphs, and then interpret that in terms of forces. That's what a force would do, and compare it with what the Feynman graph does. And that allows you to read off the force. So there. Okay. Now, a way to get a time reversal violating force is if on one end you have a scalar particle that couples to psi bar psi, and then that particle also couples to psi bar gamma 5 psi. So this particle is neither scalar nor pseudoscalar, but a mixture of both. And the fact that it's a mixture of both means that it can mediate time reversal violating interactions. It's not itself an eigenstate of time reversal. Because this one is natural under parity and this one is unnatural under parity, this exchange will also violate parity. Okay, so let's see what it looks like. So here's the Feynman graph, much easier than the triangle graph that we discussed before. We have non-relativistic spinners that we put on the ends, and they basically have a spin and then a relativistic correction, which is a spinner, two-component spinner, and then a relativistic correction, which goes like 1 over the mass and times the momentum times that spinner. In the Dirac basis for Dirac matrices that I discussed earlier. Okay, so then you just calculate. Okay, there's a propagator, which is 1 over k squared plus m squared. We're doing static exchange, so no for momentum. And you just put in the gamma 5 and fold in the spinners. I'll leave it as an exercise to you that this is what you get. Okay, you get the difference in momentum coming in here becomes a sigma dot k. That percolates from the particle into the spinners. What does that mean as a force? Well, you just do the Fourier transform from momentum space to position space, sort of invoking the inverse Born approximation, which is appropriate in this very low momentum exchange. And you can do the integral. It's a nice exercise, and you get to use Cauchy's theorem. And what you find is the force, the K is basically a derivative with respect to R. So you can pull that out and do the rest of the integral, and this is what you find for the form of the force. So it's a sigma dot R kind of force. Okay, very unusual kind of force, but very definite with a finite range. This is the prediction for what a fundamental violation of time reversal violation should look like as a fifth force. We call it the monopole dipole force because on the one side it's a monopole coupling, on the other side it's coupling to a dipole moment. So the monopole, of course, is just nothing. So, proportions. And there have been some very pretty experiments looking for this sort of thing. This is not an up-to-date. This is 2017. There are somewhat better limits now. People win prizes, like Adelberger won prizes for doing this so well. The QCD predictions, even if theta is as big as it can possibly be, the axion has a small t violation. The residual theta parameter introduces some small t violation. If it's as big as it can be experimentally, this is much bigger than it's expected to be theoretically. It would be this line. So it's not a great way of looking for axions, but it's a way of looking for surprises. And many underemployed theorists have speculated about things that would have given a non-zero signal. Don't. At least not so far. Okay. You can play the same game with exchanging particles, spin zero particles that have other kinds of interactions, and they can violate parity, time reversal, or even charge conjugation. And well, there's a table, and if you couple on one side with something like this, and on the other side with the other, you can see when you have products that are negative, you violate those symmetries. And especially intriguing are, so this of course is a 4-vector as far as relativity is concerned, but in the non-relativistic limit, it's just a scalar. So a scalar particle could couple like that. Or that's, well, it's a non-relativistic limit of the exchange of a vector particle, if you like, but it's effectively a force, and it gives you a velocity-dependent force, and this one violates P but not T. So instead of sigma dot R, you get sigma dot V. Okay, so that brings us to the threshold of experimental axion physics and the search for this wonderful candidate for dark matter, and that's where we'll cross that threshold this afternoon.
Okay, thank you, Frank. Yeah, I'm very impressed by the beautiful discussion between the fundamental electrodipole moments and chemistry.
Yeah, me too. It took me a long time to figure that out. It really bothered me.
Right. And
what
also
what the heck? What do these chemists know that we don't know?
Right. So
it turns out they do know things we don't know, but they don't know it. Yeah, that's okay.
Yeah, better we talk to each other.
All right.
Okay, so now open to questions. Any questions? Jin-Na.
Yeah.
Yeah, so hi Frank, a very nice talk. Yeah, so I'm curious, what's the role would the entanglement play here?
Entanglement?
Yeah, quantum entanglement, yeah. In all the theory here.
Well, you know, entanglement really annoys me. Yeah, I don't, nothing personal, but in quantum mechanics, everything is entangled.
Yeah.
Non-entanglement is very rare. That means you have independent things. Your two systems are independent. If they're not independent, they're entangled. So electrons in any atom are entangled. Molecules, all their degrees of freedom are entangled, and so forth and so on. This has been a feature of quantum mechanics since the very beginning. Okay, so it's these questions. So asking if something is entangled is analogous to asking whether something is classical or quantum, and everything is quantum, and everything is entangled. Okay, now you can ask if you want more particularly if there's some particular feature of entanglement that you want to emphasize, then it's fair to try to ask if some particular feature is appearing in some particular situation. Now, okay, so with that prelude, where does entanglement appear in this analysis? It's, because of course it's under the hood, because we're talking about molecules and things, so they're entangled. But if we think about what in particular is there, well, okay, maybe a good way to say it is this. When we've treated the axion cosmology, for instance, we've assumed, or in this treatment, I've assumed that we can treat it as essentially a free field. And that neglects the possibility that there are entanglements coming, or I should say, a classical field. Consider the axion background, the axion field is a classical field, except at the very end when I noted that a classical field can be analyzed as a bunch of particles. Okay, just like so. Now you can ask questions about whether the representation of the axion field as a classical field is adequate to all the kinds of observations you might want to make, or even does it change the evolution of the field in the universe? And people have studied that kind of thing, and there are some controversies about it actually, but I think the consensus is that for practical purposes, for most practical purposes, treating it as a classical field is fine. So neglecting entanglement. But I'm concerned about all the other things. I mean, I've talked about many things. And entanglement is certainly implicit in a proper treatment of several of them. But I don't think there's any, how should I say, I don't think I've been talking about anything where entanglement as such is a dominant theme. Yeah. Yeah.
Okay.
Okay. Any more questions?
Yeah.
Xinxiang?
Yeah. Hi, Frank.
Yes.
I have in your this inflation cosmological model of
Yeah.
axiom. It seems that our universe can be regarded as different domains with different condensate of axiom somehow.
In the post-inflationary,
Yeah.
in the version where inflation occurs on the pre-inflationary, where inflation comes after the condensation. Yeah, is that what you're referring to?
Inflation happens after the
Yes,
condensation.
right.
Oh, I see. Yeah.
So then we don't see. Our observable universe has derived from a small patch early on. So there's a much bigger multiverse out there that we don't have access to.
I see. So maybe my question won't make sense, but I still ask.
Okay. Yeah. Good.
My question is, what determines this scale of different domains? Yeah.
Well, that's a very good question,
Mm-hmm.
but it's really a question about models of inflation. So the answer is nothing. I mean, those models are just cooked up to accommodate cosmology.
So it depends on what experiments tell us, right?
Yes, ultimately we have to rely on experiments, and so existing models of inflation, I think it's fair to say, don't have compelling roots in fundamental physics. They're kind of you put in some effective potential and they roll down, and there are many variants.
So many parameters.
And there's even some tension with observations of gravitational waves. So we can't. So I can't really answer your question in a definitive way. Yeah.
No problem. I have one more question. Yeah. So do you this multiverse thing?
Yes.
Can do anything about this interpretation of quantum mechanics, the many world interpretation? Yeah.
Maybe, but the multiverse. So, but the quantum mechanics, in a sense, does support the existence of alternative evolutions of time and different branches of the wave function. It's a subject that is a vast subject I don't want to get into. I can't get into very deeply here, but that's kind of a multiverse in front of your face. It's not a multiverse far away. So there are several different kinds of ways in which our theoretical description of the world is much larger than what we actually get to observe. So quantum mechanical wave functions, you can't really observe all of them. You can't observe position and momentum at the same time, for instance. You have to ask sub-questions and piece together, you don't have access to the full theory observation.
Yeah, in this cosmological case,
cosmology is kind of more gross because it's just, you can't see them because they're very far away. That's right. Yeah.
Okay. Yeah.
Hello, Professor.
Yeah.
I have a question about the effect of the energy about the sigma dot E.
Yeah.
So as an analog to the energy of a magnetic field interaction with spin, we will have precession of the spin.
Yes.
So if we have a material, in some sense, have spontaneous magnetization, but with an angle, with the orientation different from the polarization, that causes precession spontaneously.
Yeah.
So with that,
if you have material that if I understand the question correctly, is if you have a transition to a ferromagnet in the presence of a magnetic field, and it's not quite aligned with the magnetic field, it will precess.
Yeah.
That's
so
in reality, of course, it would tend to relax very quickly unless you extremely careful about your choice of materials. But, yeah.
So can we consider it as a time crystal?
No. Well, you can. Yeah, you can consider it any way you want, but I don't think it has the really characteristic properties of time crystal of being rigid against many kinds of perturbations, but susceptible to perturbations that restore time translation symmetry. I didn't really get to talk about that. Remember that lecture? That was a piece I didn't get to give. But maybe if we have time later, we can come back to it.
Thank you.
Well, I forget. I've given so many talks. Did I show you the magnetic spoon?
Yes, you showed.
Yeah. Okay. So that's the thing. If to me the essence of spontaneous symmetry breaking is shown by the ancient magnetic spoon that is magnetized. Okay. So you can do lots of things to that spoon, and it still remains a magnetic spoon that tells you the direction of the field. So you can do all kinds of local perturbations. You can heat it up as long as you don't heat it too much, and it stays a magnetic spoon with the same orientation. But so it has a kind of rigidity to it because it has long range order, and no local perturbation can upset that long range order. But if you apply a magnetic field to the whole thing, the spoon will easily reorient itself because that is the way that the symmetry told it cost zero energy. So a combination of rigidity against local perturbations, but susceptibility to certain kinds of perturbations that restore the symmetry. That to me is the essence of spontaneous symmetry breaking. And it doesn't have to be a continuous symmetry. It certainly doesn't have to be rotation. It could be also a symmetry that is broken time translation symmetry. In that case, the relevant perturbations analogous to a magnetic field would be some AC signals that restore the broken symmetry. Global AC signals.
Yeah. I think Frank, you wrote a few public articles that explain the physics of time crystals.
Like over time, I've come to understand it more clearly.
Right. In Wall Street Journal.
And it's been a somewhat controversial field with different people having different definitions of time crystals. So I think since I introduced the name, I get to choose at least what I think is the main point. And I think the main point is that you want to have a system that's rigid under many kinds of perturbations, but sensitive to perturbations that restore time translation symmetry.
Yeah. Okay. Any more questions from students? Mm-hmm. So maybe I can ask the last question. So you mentioned this axion is a boson, and they can mediate the fifth force.
Yeah.
And by the way, this also tested in China, in USDC, that people use NV center to test the fifth force.
Right. Yes, very good.
And since also axion is a scalar, it's a boson. So, but when the universe cools down, you can imagine the boson can condensate.
Yes. It does condense. Right. I mean, it's a scalar. It's a classical field.
Right. So
that is a condensate.
Yeah. Maybe you can.
as at least in the early universe, when the field is coherent, because the universe was pretty smooth and so forth, then it was literally a Bose-Einstein condensate. It's a scalar. It's a classical field. Now later on, the universe developed as things slosh around. There are all kinds of interactions. It's not clear how much of that coherence is maintained. There's some controversy about it, but it starts out as a very cold Bose-Einstein condensate.
I see.
Because it's very uniform, and
right. Yeah. For condensed matter physics, we like to see the Bose-Einstein condensate.
Yes.
Okay. Any more questions? Now we see there we have also very little audience. That's very cute there.
Oh yes.
你有什么问题吗？ Okay, he think you're very clear. Okay. All right. All right. So let's see you in the afternoon, 2 o'clock, the same room. Okay. Thanks, Frank again.
Thank you. Okay.